Good morning, good afternoon, good evening, wherever you are located, and welcome along to the AMETEK Solid-State Controls webinar this month for May 21st, 2025. Thank you very much, everybody, for joining us today. We really do appreciate it. As always, we'd like to start off by saying, if you can hear my voice, please go into the chat on the right-hand side of your screen and type in there that you can hear me. That way, I am not speaking to myself, which I do many times, and people think I'm crazy, but I don't want to do it on the webinar. So please let me know if you can hear my voice. And while we're waiting on those replies, oh, you can hear me. Thank you very much. And I appreciate that. Andrew, thank you. Martin, perfect. Jim, absolutely perfect. So today we are going to discuss why we need a UPS system. Okay, obviously there are UPSs out there. We manufacture an industrial UPS here at AMETEK Solidstate Controls, but you know, it's very good to know the background of why we need a UPS in the first place, and you know, what the gap is that the UPS fills. Okay. So we'll do a little bit of housekeeping before we go any further. Obviously, my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls, working out of the Stafford, Texas office. So that's just on the southwest side of Houston. So that is where I am located. I've got 24 plus years in the industrial UPS industry, varying from the oil and gas platforms off the east coast of Scotland, all the way to the petrochemical plants in Houston, Texas, and the surrounding area. I've worked with all major UPS charger manufacturers. In my time, I've worked with the majority of our competitors, but it's the last 8 years that I have spent now with AMETEK Solid-State Controls. There will be a lag of around 30 seconds between you hearing my voice and me seeing a question. Basically, we use a platform called Webinar Jam, and it converts the video and the sound into a signal that Android devices, iPhones, and Windows-based devices can all basically show. So there is a little bit of processing time, and it's around about 15 seconds. So what I ask is, if you have any questions, if you look on the right-hand side of the screen, you will see the chat bar, and in the chat bar there is two tabs. One is chat and one is Q&A only. If you have any questions at any point during the presentation, go into the Q&A only and type it in, and then at the very end I'll go through all of the questions that have been asked and hopefully answer all of those questions. It just makes it a lot easier, rather than me speaking and then, you know, 15 to 30 seconds later after I've said something, that's when the question is going to pop up for me to answer. So it doesn't make sense me answering them as I go. Another question is, will the webinar be recorded? And absolutely, yes, the webinar is recorded. Webinar Jam does record the webinar. And they actually have a new feature where you can go back and watch it using the link that you will be sent after this webinar, saying thank you for joining us, and you can replay and watch the webinar back. But what our fantastic marketing team do is they go in and they convert this video into an MP4 and then upload it to our YouTube channel. And they usually do it probably within 24 hours, and that allows you to share to anybody you want. It's a publicly accessible YouTube channel. Thank you, Amina, for putting that up there. There is the YouTube link, and that link has a link to all of our other videos that we've done over the last few years that we've been doing this webinar. So a lot of good information on there. And also, the webinar should last around about 45 minutes to an hour, depending on how much I speak, which is very varied, and also on how many questions that we get at the end. Okay. If Naren, thanks for the comment. You say the slides are very light. I would imagine that may have something to do with the graphic settings on your side. There's been no changes in our settings here, so hopefully you can get that taken care of. Okay. So what are the learning outcomes today? So we want to understand why we need a UPS system. We need to know the difference between a UPS and a generator. And we need to understand how a UPS works. Okay, so that is going to be the three objectives that we have today. So first of all, we need to go back to the very basics, the very beginning, and we need to understand what AC is. Okay, and I know most people in this webinar know what AC is, but I want to drill down just a little bit so we can understand the difference between AC and DC and how it affects different loads and all that kind of good stuff. So for an AC current, that means basically that the current, we say that it's alternating, but what it does is it moves in basically two directions. And don't mix up the amplitude of the current or the voltage with the direction of the current and voltage, which is a very, very common misconception. Okay, so for this portion of the sine wave here, okay, we can see at this very starting point here, we're at the zero crossing point. There is no potential, there is no voltage available to do any work at that point in the sine wave. And then what happens is the amplitude of the voltage starts to go up, not the direction, the amplitude, okay? So if we looked at any current that was flowing due to this voltage, we would see that it is moving this direction, okay? And as we go further up to the top of the sine wave, that is just saying that the potential of the voltage is at its highest point. And then when the voltage starts to come down again, once again, that's not the current changing direction. We have not changed the direction of the current yet. The amplitude of the voltage driving the current is just coming down. The current will still move in that direction. Okay, so for the whole portion of the top half of the sine wave, the current does not change. It is not alternating. It is only when we go to this portion of the sine wave and we go past this zero crossing point, that is when the current changes, and basically it will move to that direction. Now, as we mentioned before, the amplitude of the voltage, in other words, the driving force behind the current, the amplitude changes, but the direction doesn't. It only does that at the zero crossing point. So we're going this way for that portion of the sine wave, and obviously this way for that portion of the sine wave. And it does that at 60 times a second in North America at 60 hertz. Okay, so we're basically pushing and pulling current through the conductors and through your load circuits. It's basically pushing forwards, pulling backwards. That's what we're doing all the time, and that is why we call it AC, alternating current. And I do like to go over this because it's a good reminder of why it is alternating current. And I think this is an excellent slide to show you how that is generated at the power plant. Now, obviously, I'm not going to go into renewables and how solar panels do it and how wind turbines do it. This is basically how turbines, steam generators, basically the mainstay of the electrical grid, the rotating machines that create the majority of the energy that we use in all over the world. Okay, So first of all, we need to understand how a generator works. And most generators will have a stator and they will have an armature. Now, the stator is static. In other words, it doesn't move. And the armature is what is moving. And the stator is basically, you just look at it as a magnet. And it has a north pole and it has a south pole. And then the armature is basically rotating around this axis here. And then this, the waveform on the right-hand side, that is at all the different stages through the rotation through the magnetic field of the stator. Okay, so if we start at point A, which is this zero crossing point here, you can see distance-wise, it's equidistant from both the North Pole and the South Pole. In other words, it is as far away from the poles as you can possibly get. And at that point there is no voltage being generated. There is no mutual inductance happening inside the machine from the magnet into the armature. Okay, it's too far away from the poles to generate anything at this point here. So that's why we have no voltage available at point A. And you can see the direction of this spinning shaft here. We're moving counterclockwise. So our next point is going to be at point B, which is 45 degrees within the sine wave. Okay, and that is this point here. And you can see that that relates to that point there along that graph. We are now getting closer to the north pole of the magnet, and therefore the magnetic field is starting to build in the armature and is generating a potential. Okay, so we are starting to generate voltage at this point. And remember, it's not a step. As we move from A to B, it is a gradual increase, and it's a sinusoidal increase, okay, from A to B there. And then when we get to point C, which is 90 degrees within the complete 360-degree spinning of the motor, then we are as close to the North Pole as we can get. So that is where the most potential in the sine wave is created. Okay? We are as close to that magnet as we're going to get. So that is the most potential. It is the most magnetic field that we are going to build in that armature. And remember, at this point here, the current is flowing in one direction still, okay? And then when we get to D, we're starting to move away from the pole again. So we're starting to lose our amplitude. The direction of the current is still the same, but we're starting to lose our magnetic field. And then obviously when we get to point E, we are as far away from the north and south as we were at point A. So that is the other zero crossing point within the sine wave. Okay, and then it starts all over again, but now it is the south pole of the magnet that is acting on the armature. The field reverses and the current reverses. Now the current will start to flow in the other direction, giving us our alternating current. And as you can see, we've got F and then G and then H. Does exactly the same. It builds the potential sinusoidally out of that spinning motor. Okay, and then obviously you know what we're depicting here, the motor spins and it's powered by either gas, oil, could even be steam, but then we connect a generator to that shaft, and that is what this is. This is a generator, the electrical generator, where we generate the electrical field in the armature. So that is how AC is created at the power plants. And that is why we have sinusoidal waveforms coming out of the socket in our walls, because that is the exact way that the motor spins. Now, I know this seems quite obvious, but there is no device known to man that can store AC power for prolonged periods of time. Now, if somebody just raised their hand there and says, I've invented something, then keep quiet, go to the patent office and write up your patent, and you will become a billionaire, a trillionaire. If you figure out a way to store AC power for prolonged periods of time, then you have solved a problem that the world has had for a very considerable amount of time. And I wish you great luck with that. And I would love to invest in that company too. Okay. And then the next question is, well, why can't I just use a generator? I don't want to use a UPS. Can't I just use a generator? Now, generators are actually very, very good. You can have a generator outside your house. You can have a generator at the power plant, at your petrochemical plant or your oil and gas installation, wherever it is. You can use generators, but generators have a downfall. And that downfall is that they are not instantaneous in starting and coming up to power. Okay, they need time to get started. And the problem with that is whenever we have a power loss, and you can see in the picture here, that can be whether a power pole goes down from a weather event or whether it's physical damage to the power pole, like a car crashes into it, or whether there's a fire at the substation in the transformer. Whatever the reason is, we do not know when the grid is going to lose power. It's very, very rare that we know the exact time that the grid is going to lose power. So there's no way we can preempt the starting of a generator to cover any power issues that we're going to have. It's retroactive. The power outage has to happen. We then have to sense that power outage, and then we have to start the generator and get it up to speed. Now, if you knew when it was going to happen, it would be absolutely fine. If you had a crystal ball, it would be absolutely fine. But we don't. We just don't know when these power outages are going to happen. Okay, and in your house, that's not such a bad thing. If you had a generator outside, 30 seconds to get a generator up to speed after a power outage isn't the worst case scenario. Okay, because your house, the loads inside your house that we care about are going to be your refrigerator, your lights. Maybe if you bought a big enough generator, being able to run your HVAC system, and especially in Houston in the summer, it would be good to have some form of AC. They are the main things that we're trying to power from a generator. And 30 seconds without lights, yes, it's an inconvenience. You may have to have a flashlight for a moment, or you can just sit and wait for the generator to come on and get the lights on. But it's not critical. Your generator is going to start. Your lights are going to come on at some point. And obviously also within your refrigeration system, whether it's your fridge or your freezer, they are insulated. So 30 seconds to a minute for a generator to start, they're not going to lose any temperature whatsoever. So that's not an issue either. So within your house, that's why you shouldn't have a UPS at your house, basically. It's because you can use a generator, and all your loads will handle going off for a period of time before the power comes back on once a generator is up to speed. So the house, absolutely fine. But when it comes to a petrochemical plant or a refinery or anything else that has critical equipment that needs to run 100% of the time without any blip in power whatsoever, then we have an issue. Okay, like this picture here is an offshore oil and gas platform, and they are watching the screens, and these screens are connected to analyzers, pumps, motors. They have to know what is happening in the plant at all times. We have level gauges here that are all connected to alarm thresholds. So if a pressure goes beyond its alarm level, we need to know immediately, so we can either close a valve and prevent it going higher in pressure, or even open a valve and vent out to a flare stack. We have to be able to monitor this at all times within the control room. And if we lost the screens, or if we lost power to the analyzers that sends all the information to these screens, then we're in a very bad situation, indeed. Okay. We can't lose power to these screens because we need to know at all times what is happening in the plant for safety and for process control. Okay, if the DCS system, which is the distributed control system, loses power, you're not able to control pumps or solenoids or other devices. And these systems, they'll be designed that they will go into their fail-safe mode, which usually means a controlled shutdown. So if we lose power to any of these extremely critical pieces of equipment, they're going to go to their fail-safe shutdown mode, and the plant is going to shut down. Okay, which is obviously costs millions of dollars in some respects. If an IT system loses critical data, then that's very bad as well. When the power goes off, we could lose critical data because the system didn't shut down in a controlled manner, and save all the data that it needed to save. We also have turbine control systems. So all of the control systems at the power plant that is monitoring the speed and the temperature of the turbine and making sure that the gas flow and the exhaust temperatures are all exactly what they need to be. If we lose sight of any of that, then the turbine is going to go into a controlled shutdown, or even it could go into an uncontrolled shutdown if we lose complete power. Fire and gas detection. If we lose the ability to detect fire or gas releases, then we're going to shut down the plant in those circumstances, because we don't know if there is a fire or gas release. The system will go to fail-safe mode and shut those systems down. And there are just many, many other systems out there that require constant, uninterrupted power. Okay, and in a data center, we talked about that was in a petrochemical plant or a refinery. Even in a data center, and this is a picture of what the inside of a data center could look like, they cannot lose power, okay? Because the negative consequences of downtime in a data center is enormous. Because remember, the cloud is, your data doesn't live in the sky. I know this is news to you. I apologize that the cloud doesn't exist, but the cloud is thousands of data centers all over the world. Pretty much every city in the world has data centers, and they are huge. They use a huge amount of power, and that is where all of your cloud-based data lives, in a data center. Okay, if we lose power to that data center, then it's not just lost revenue, because the people don't have access to their stored data. There are service level agreements that companies have with these data centers, banks especially. They need to know that the money getting pushed around the world can be tracked and can be done at all times. So they have service level agreements that say, hey, we want 100% uptime. And if you don't meet that 100% uptime, then there are going to be financial penalties, because it would, let's say, for example, Chase Bank, if their system went down for 30 minutes to an hour because of a data center failure, they're going to say, well, wait a minute, we couldn't do anything for 30 minutes to an hour. Our customers couldn't do anything for 30 minutes to an hour. And our reputation and trust will suffer because of that. So there are extreme penalties to data centers if they don't remain online all the time. Also, that's for power outages. UPS systems also prevent any sudden power interruptions that could cause data corruption and loss. Because if the servers aren't shut down in a controlled manner, then if they didn't save the last point that they were at, you don't know if a transaction or something is being done at the moment the system shuts down. That data gets lost forever because it wasn't able to be saved. So data could be corrupted, data could be lost. It's a very bad situation. And also, you know, if you have clean and stable power, that can extend the lifespan of servers, networking cables and equipment, storage devices, and other sensitive electronics. So, you know, a UPS prevents brownouts, peaks, troughs, bad things, bad power condition coming from the grid from getting to the critical equipment and causing any issues. So there are huge issues why we can't use generators, and it all boils down to computer power. Okay, everything within your computer, everything within a data center, everything within a distributed control system is all powered not by AC. I know this is going to come as a surprise to some people. It's supplied by DC. Okay, so when you plug in your laptop, when you plug in your desktop computer, you're taking AC from the socket and it's being converted back into DC. And then the DC is what is controlling all of the processors, the RAM, and all that good stuff inside your computer. It's not using AC whatsoever. It's using all DC to power all of the computer components within the system. And that's the same with DCS, distributed control systems. They use banks of power supplies that take the AC and convert it to DC to supply all of the DCS loads. Okay, so I know it sounds strange that your UPS takes AC, converts it to DC, then it takes that DC, converts it to AC, and then that AC then goes out to our load circuits and gets converted to DC again. But that is what we need to do. And this is in a data center. This is a power rack in a data center. And it's just loads of AC to DC power supplies that then go on to feed all of the server racks and stuff inside the data center. Okay. So loss of power to a computer for more than a second, depending on the capacitors in that DC power supply, means everything shuts down, and everything shuts down in an uncontrolled way. Data will be lost. Okay. So for oil and gas plants, they'll typically have a UPS that supplies from 30 minutes up to 3 hours of power. And that's basically so that the plant can be shut down to a safe mode of operation when the grid power is lost. They can put the valves in the position, they can vent any gas out to the flare stack, they can release pressure in vessels, everything that they need to do to get the plant to a safe mode when the grid power is lost. That is what the UPS is there for. Basically, it's usually 30 minutes to 3 hours of time required. Okay, hopefully the power comes back before that 30-minute or 3-hour time expires. But, you know, that's what a UPS is usually designed for in an oil and gas plant. In a data center, the UPS is for a much shorter period of time. It's actually usually around about 5 minutes that the battery is sized for, because for a data center, we're talking megawatts of power. Okay, a huge amount of power. And to have a battery to back up that huge amount of power for a considerable amount of time, the battery would need to be huge and extremely expensive. Okay, so what a data center does is they have either one or many emergency standby generators that are designed to run the full data center if there is a power outage. But as we mentioned earlier, the standby generator needs time to first get the signal to start. So when power is lost, a signal is sent to the standby generator. Okay, you need to start up. So then it starts up, it rotates, and it gets up to speed. And then it uses its feedback circuits to say, okay, am I fast enough? Am I at 60 hertz? And is my voltage okay? It does all of its checks. And that can take anywhere between 30 seconds to 5 minutes to completely get up to speed and be ready to go online. And then only after the emergency standby generator says, right, okay, I am good, will an automatic transfer switch in the system say, okay, I'm going to transfer over to my emergency standby generators, and all of the power will transfer from the UPS to the standby generator until the grid power comes back on. So the UPS at a data center is only there to cover the period between the first loss of power and the time that the emergency standby generators get up to speed and can be put online. Okay, it's not for a prolonged period of time. It's only for that short period of time between loss of power and generator up to speed. Okay, so maybe an obvious question, but what makes a UPS uninterruptible? It's a good question. Okay, and it's quite simple. It is a battery. That is the only thing that makes a UPS uninterruptible. We can store power in a battery for later use if something goes wrong. It is the only way that we can store power reliably. Okay? And remember the difference between AC, alternating current, and DC. So this is the waveform for DC. Now, you're shouting, that's not a waveform, Craig, that's just a straight line. Well, it's still a waveform. It's just a waveform that is not changing. Okay? So, you know, most of our systems run at 135 volts DC. So the voltage level here to this orange line is 135 volts and never changes. Okay? If the system power is on, and the current never changes either. Okay, we don't go past this 0 volt line, so the current is all going in that direction. Okay, so it is direct current, it never changes direction. This orange line here would have to go down to this side of the waveform for the current to flow in the opposite direction. And a battery will never, ever do that. Okay? Power only flows in one direction, direct current. That is where DC, the term DC comes from. Okay? So the problem solved. Let's just convert AC to DC. And that's it. That's all we need. Well, unfortunately, if you go back to when electricity was first invented, there was a battle between Tesla and it wasn't Westinghouse, Edison. I can't remember. I'm put on the spot. I can't remember. This here is the important part. Tesla won. Okay, AC won. So all of the power that goes to our houses, to our petrochemical plants, to the refineries is AC. Why did AC win? Well, because it's so much easier to transform the voltages on AC, okay? And that's important when you are sending electricity around the country, because what you can do is at the power generation plant, you can pump up the voltage to a very high voltage level, which means you don't need much current flowing through the conductors, okay? Because conductor size is what will restrict the distribution system. If we had to use really thick conductors all around the world, then it would be extremely expensive. The amount of copper we would have to use, or aluminum, whatever they use these days, you would have to use a huge amount to be able to carry that amount of current. So the higher the voltage we can send over the distribution lines, the smaller the current, and therefore the smaller the cables and the smaller the losses as it gets sent around the country. So it's just easy to do with a transformer. You know, there's no electronics involved whatsoever. You just put it through a transformer. You can step it up to the voltage that you want, or you can step it down to the voltage you want. Very, very simple. And you can see why AC won all those years ago. But the problem is, we need to now be able to take that AC and then convert it to DC. And to do that, we use a rectifier or a battery charger. And what we do is we take the primary AC supply. On our industrial systems, we go through a transformer, and then we go through a rectifier bridge. And that converts the AC here into DC here. And its sole purpose is to keep the batteries charged at the level that the battery manufacturer stipulates the batteries should be charged at. Okay, a lot of people think that the voltage that the charger rectifier creates is, because we're going to actually add an inverter on the output here in a minute, is specifically the voltage that the inverter needs, but it's not. It's got nothing to do with the inverter. It is the battery. So let's say Enesis, which is one of the major industrial battery manufacturers, say, okay, if you have a 60 cell lead acid battery, then you're going to have to float charge your system at 60 cells times 2.25 volts, which is what they usually stipulate at 77 degrees Fahrenheit, which equals 135 volts DC. So the output of our rectifier charger is specifically chosen only to charge the battery. That is the most important thing we're trying to do. Keep the battery charged optimally, okay? Not overcharging it, which can cause it to dry out or boil off electrolyte, or if it's a valve-regulated battery, eventually dry out the electrolyte inside. Or if it was too low, it would undercharge the battery, which would cause sulfation of the plates and would eventually cause the battery to fail and wouldn't have any capacity. So it's very important we charge the battery at the correct voltage. So that is the only parameter that we care about when we're charging the batteries. That's what the charger is doing. It is there solely to charge the batteries, okay? But then we need to invert that DC back into AC, because remember, all of the equipment that is connected in data centers and in petrochemical plants uses AC. Now, yes, I do understand that we then usually always take that AC again and convert it back to DC in the power supplies for the DCS, the screens, the computers, and all that kind of stuff. But we always distribute using AC because Tesla won. So the inverter is designed to say, okay, well, my battery is going to work within the realms of, if it's for that 60 cell system, it's going to work anywhere between 105 volts and 140 volts. Okay, 105 volts is the low voltage cutoff for a lead acid battery, and 140 volts is usually the highest voltage you will use to equalize the batteries if you have a wet cell battery. So our inverter is designed to operate within those two set points, okay? So we convert that DC that goes into our inverter, so it's DC here, and on our output, AC comes out. Now that can be single phase, three phase, whatever you require, okay? So that's why we created the double conversion UPS. So we just put it all together. We have our AC input coming in here from the grid. It goes into our rectifier battery charger. We have our battery connected here. We then have our inverter, which takes the DC and converts it back into AC. That then goes through a static switch. If you want to know what a static switch is, you can watch some of our other videos that we have on our YouTube channel, and it goes into detail about what a static switch does. But basically, it's a switch that has no moving parts and can choose between the best source of power. And it does everything it can to basically always stay on inverter unless the inverter fails. And if the inverter fails, it will then transfer to an alternative source. Okay, so that is a double conversion UPS. So how does the battery charger do it? Well, every parameter, remember, is dictated by the battery, as I mentioned before. So what we do is we use a 6-pulse fully controlled rectifier. And when we say 6 pulses, it means we have 6 SCRs in our bridge. Okay, and we take our 3-phase input here and we convert that into DC, depending on the battery. And remember, for a lead acid battery, the nominal cell voltage is 2 volts. For a NiCad battery, usually the nominal stipulated voltage is 1.2. For lithium ion, it can be anywhere between 2.4 and 3.8. Okay, and down here, this tells you roughly what most of the battery manufacturers will stipulate, how many cells they will put in an industrial string. So for lead acid, it's 60 cells. The nominal voltage will be 120 volts, but the float voltage will be 135 volts. For an NiCad battery, you're probably going to have 96 cells. That's going to be a 115 volt nominal voltage, and the float voltage is going to be around about 136.2. And for, let's say, for this NEMI nickel metal metal hydrate battery, it's going to be 96 cells, 115 volts nominal, 136.2. And then for a NiCad lithium ion, for a lithium ion battery, should I say, it may have 35 cells at an 84 volts nominal voltage, but it gets charged at 126 volts. So the charger has to be able to do different voltages for different types of batteries. Okay. And then the inverter just takes that DC, and it has to be designed to accept the full range of voltages from that battery. And as I mentioned, for a lead acid, it's going to be 140 volts for equalize down to 105 volts, which is the end of discharge for the battery. Once again, Enesys, the manufacturer, may say, okay, at 1.75 volts, we say that is the end of the discharge. There's a little bit of a safety margin there. You can usually go down to 1.6 if you really wanted to, but you want to stay away from that if at all possible. So they'll say 1.75, and if you multiply that by 60, you get 105 volts. And then what the inverter does is it creates a synthetically generated sine wave at the exact frequency and voltage required. So for North America, for a single phase system, it's going to be 120 volts at 60 hertz. In the UK, it's going to be probably 230 volts at 50 hertz. Depending on where it is going in the world, the frequency and the voltage can be changed very easily at the design stage of the UPS. An inverter, rather than use SCRs like the rectifier bridge did, what it does is it uses IGBTs to change that DC into AC. And it's quite simple. What it does is it switches the IGBTs, the transistors, on in a certain way to get AC from DC. So basically, you can see here, we have this IGBT turned on, and it will make this side of the transformer positive. But remember, we do have to have a return path to the negative. So therefore, we also switch on this IGBT, and that makes the negative get to the bottom of the transformer. So obviously, they are both going to be turned on at the same time, and it will give us a square pulse on the input to the primary of the transformer. And then what we can do is then switch the other two IGBTs on and these IGBTs off, and it swaps the polarity of the transformer. You can see that the positive now goes down through here and down to this side of the transformer. And if you follow the negative, it goes through this transistor and gets to that part here. And that gives us a negative pulse on the input to the primary of the inverter transformer. And if you put the two together, if you switch those two IGBTs at 60 hertz, you would get a 60 hertz square wave going into the primary of the transformer. Now, that's not what we do in our IGBT PWM systems. What we actually do is we use a PWM waveform, and we're switching at 8 kilohertz. We're still creating a 60 hertz sine wave in North America, but we're using an 8 kilohertz carrier wave to create PWM at 8 kilohertz that goes into the primary here. And then we use the inductance of the transformer, this inductor here, and this capacitor here, which changes the PWM into a beautiful synthesized sine wave that is absolutely perfect in every way. And it's all for this if power is lost to our UPS system. If power is lost, the rectifier turns off and the battery just continues supplying power to the inverter. A lot of people say, okay, it switches to battery. It doesn't. Our systems do not switch to battery. There is no switching involved whatsoever. Basically, the power from the charger disappears and the battery is in parallel with that charger and just continues to supply the inverter. The inverter doesn't even know that power has been lost. The system as a whole will, but the inverter just cares that its voltage needs to be between 105 and 140 volts. And it says, if you give me that, I'm going to create perfect 120 volts 60 hertz AC for a single phase system in North America, and I don't care what anything else is doing. It's going to be a perfect sine wave. That is how the system is designed. And power will flow from the battery through the inverter, through the static switch, out to our AC outputs, and your output, your load circuits will not see even a minute blip. You could analyze it down to the very smallest portion of time, and you will not see anything because the battery just continues supplying power to the inverter. Our output is uninterrupted. Okay, so that's pretty much why we use a UPS in industrial and data centers. So thank you very much for watching all the way through. Really do appreciate it. And now what I would like to do is see if there are any questions. Okay, a lot of people were saying the slides were faded. I'm going to have to see why that is, because there are no different settings that I have done. I do apologize if the slides seem faded. I'll check with Webinar Jam after this webinar and see if they have changed a setting somewhere. So I do apologize for that. And I'll also watch the video back to see if I can see what the issue may have been. But hopefully you could still follow the webinar as we went through. Okay. I don't see any questions coming in. So I also like to mention that the last slide looks normal. Thanks, Jack. We get all the way to the end and the last slide looks perfect. Oh, great. So we do send out a survey to all of our attendees and to all those who registered. And it's very important that, I think it's the 5th question within that survey, asks for what you would like us to discuss at the next webinar. And I really do look for feedback on what items to discuss, because I can only come up with a certain amount of things, and the things that interest me. And remember, I live in the UPS world, so I'm so ingrained in this world, I don't quite see issues from our customers or the end users. So for you to give me feedback and say, okay, you know, this is what I need to know about UPS systems, then I can tailor the next webinar to cover that. That, if you can take time to answer the survey, it would be truly appreciated. And also, don't forget, you know, AMETEK is one of those old-fashioned companies, AMETEK Solid-State Controls, where we still have a phone number, and you can still call up, and yes, there is a menu tree, and you have to press 1 and 3 or something a couple of times, but you will get to a human being, okay? And that human being is there to give you technical help. You will be routed to your the area technical manager that you're at. And if you don't want to talk to us on the phone, you can go to our website and use our contact us page, or you can even go to our YouTube channel and watch some of our YouTube videos. Okay. So we do have some questions. So first of all, if your load at the AC output is a constant and your inverter input receives 105 volts, what would be the effect of the current? I would like to assume that the current would need to increase in order to supply the same power. And that is correct, Manuel. Yes. So as the voltage of the battery starts to go down, so let's say for ease, we're using 10 kVA, sorry, 10 kilowatts of power. And let's say we're doing 100 volts. Then that's going to be 100 amps. But as that voltage goes down, and just for ease of calculations, if that voltage went down to 50 volts, we still need 10 kilowatts. So the current would go up to 200 amps. So yes, as the battery starts to deplete, the current required by the inverter starts to go up. So that's why it's very important when you get somebody in to do a capacity test on your battery, and it's a battery for an inverter. If you're running the inverter as the load for that battery capacity test, they have to understand the intricacies of a constant power capacity test rather than a constant current capacity test. So a very good question. We are at a time where we have to change the transformer used in our inverter. We have purchased the recommended transformer. Does your group help with installing it? Michael, yes, they do. If you contact us using the telephone number above or through the email system that I mentioned before, then yes, our guys, we replace the ferro-resonant transformers on a regular basis. So we would definitely be able to help you out. Andrew Kersey asks, do you all see many flywheel UPSs these days as opposed to a battery? Andrew, no, not really. There is one company in North America, I think their name is Pillar. They were big into the flywheel UPS systems. And in truth, they didn't gain a lot of traction because, as with anything that has moving parts, bearings will go, they're hard to maintain. There's a lot of moving parts and a lot of mechanical things that can go wrong within a flywheel UPS. So we don't see many flywheel UPSs out there. Okay. So some good questions there. So we've got a few minutes left, so I'll give you an opportunity to ask any more questions if you have them. But in the meantime, I would just like to say thank you once again for taking time out of your day. And I know most people have an extremely busy day, and for you to take 45 minutes to an hour out of your day to listen to me basically jabber on about UPSs, we really do appreciate that. And we hope you get some good knowledge out of these webinars. That's basically what we want to do. We want to arm you with some good knowledge so you can make good decisions as the end users of our UPSs. So we really appreciate you taking the time out of your day to watch and listen to this webinar. Once again, I do apologize if the slides were very light. I will get with the company and figure out what may have happened and how we can prevent that. I do know that I just moved to a brand new laptop to do this, and I don't know if that maybe caused some issues. It shouldn't have, because this is a cloud-based webinar service, but hopefully we can improve things for you. So don't see any more questions. I'm not going to drag this out any longer. We appreciate it. Please take a moment to answer the survey and let me know what you want me to discuss next month. And until next month, have a great end of your week. Have a great month and take care. We will speak to you again soon. Thanks very much, everyone.